Hello, and welcome to Boring History for Sleep. Tonight we will be exploring a subject of quiet, unassuming importance. Imagine the retail floor of a grand department store in the 1930s. Sunlight streams through tall windows, illuminating displays of woolen coats and silk dresses. A customer, considering a purchase, reaches for a small, cardboard rectangle attached to a sleeve. It is not held by a familiar plastic loop, but by a small, sharp, nickel-plated steel pin, pushed directly through the fabric. Removing it required a careful, deliberate pinch and pull, a tiny act of caution repeated thousands of times a day, a small potential for a snagged thread or a pricked finger. This simple, sharp object was the ubiquitous solution of its time. But how did this seemingly mundane object, the price tag fastener, evolve from a simple piece of sharpened wire to the sophisticated, standardized systems we know today? To truly understand its significance, we need to examine its quiet, meticulous, and profoundly unexciting origins. The story of the standardized price tag and its attachment method is, in essence, the story of the modern American department store itself. Before the late 19th and early 20th centuries, retail was a far more fragmented and personal affair. In small dry goods stores, general stores, or tailor shops, prices were often not fixed. They were subject to negotiation, or items were simply kept behind a counter, with the proprietor retrieving them and stating a price. When tags were used, they were inconsistent, often handwritten on simple paper squares and attached with whatever was on hand, a piece of twine, a common sewing pin, or perhaps simply tucked into a pocket or fold. There was no system, because the scale of the operations did not yet demand one. The rise of the great department stores like Macy's, Marshall Field's, and Wanamaker's changed this dynamic completely. These were vast, multi-story palaces of commerce, offering an unprecedented variety of goods under one roof. Their business model was predicated on high volume, fixed prices, and allowing customers to browse freely among the merchandise. This new way of shopping created a new set of logistical challenges. With thousands and eventually millions of individual items on the sales floor, a reliable, consistent, and efficient method of marking each one with its price and stock information was no longer a convenience. It was an operational necessity. In the 1920s, the dominant technology for this task was the humble pin. This was the first era of true, albeit rudimentary, standardization. The primary tool was the T-pin. This was a variation of a standard straight pin, but with its head formed into a perpendicular bar, creating the namesake T-shape. This design offered a distinct advantage over a simple straight pin with a small round head. The T-bar provided a larger surface area, making it easier for stock clerks to handle and preventing the pin from pulling completely through the small hole in the price tag. It also offered a slightly more secure anchor in the fabric of a garment. The material specifications for these pins were a matter of practical concern. Early T-pins were typically made from a high-carbon steel wire, often designated as Type 1060 or 1070 steel. This type of steel was chosen for its ability to be hardened and tempered to hold a sharp point, a critical feature for easily penetrating fabrics, especially the heavy wools and dense cottons common in the era. The wire was drawn to a specific gauge, typically between 0.6 and 0.8 millimeters in diameter, a balance between being thin enough to minimize fabric damage and strong enough to resist bending during insertion. After being cut to length, typically between 1 and 1.5 inches, the pins underwent a pointing process where they were ground to a sharp conical tip. The T-head was formed through a mechanical stamping or bending process. However, a plain steel pin was susceptible to rust, which could stain garments and was a significant concern for retailers. To combat this, the pins were almost universally plated. The most common plating material was nickel. The nickel electroplating process involved submerging racks of the steel pins in a nickel salt bath and passing an electric current through them, depositing a thin, bright, corrosion-resistant layer of nickel onto the surface. This gave the pins their familiar silvery shine and protected the merchandise from rust spots. In some higher-end applications, brass pins were used, as brass is inherently corrosion-resistant, but the higher cost of the material made steel the industry standard. The tags themselves were also becoming more standardized. They were typically die-cut from a heavy cardstock, often referred to as tag stock or caliper board. A common specification was a 100-pound or 120-pound stock, which referred to the weight of 500 sheets of a standard size. This provided the necessary rigidity to prevent tearing and creasing. The stock often had a high percentage of rag content, meaning it was made from cotton or linen fibers, which made it more durable and resistant to tearing at the pinhole. The surface was usually finished with a clay coating or was calendared, passed through heavy rollers, to create a smooth, non-porous surface suitable for writing or stamping. A single, small hole, typically 1/16 or 3/32 of an inch in diameter, was punched near one end of the tag. The process of attaching these tags was entirely manual. A stockroom employee would take a garment, a price tag, and a T-pin. They would push the sharp point of the pin through the hole in the tag, then carefully guide the pin through a small portion of the garment's fabric. The preferred location was often a seam, the underside of a collar, or a placket, where the small hole created by the pin would be least visible. The clerk had to be careful to pick up only a small amount of fabric to avoid creating a pucker, but enough to ensure the tag was secure. Once the pin was through the fabric, it would simply lie flat against the garment, held in place by the T-head on one side and the friction of the fabric on the other. An alternative, and often considered safer, option was the safety pin. Small, nickel-plated safety pins offered a more secure attachment, as the pin was fully enclosed, eliminating the risk of it falling out or the sharp point being exposed. However, safety pins were more expensive to manufacture than T-pins and required a two-handed operation to open and close, making the tagging process slower and more laborious. Consequently, they were often reserved for items that would be handled more frequently by customers, or for heavier garments where a T-pin might not be secure enough. This pin-based system, while a significant step up from the ad hoc methods of the past, was fraught with minor but persistent problems. The first and most obvious was fabric damage. Even the sharpest, thinnest pin created a permanent hole in the fabric. While careful placement could hide this, a misplaced pin in the center of a silk blouse or a fine knit sweater could render the item unsellable. The risk of snagging was also constant. The exposed shaft of the T-pin could easily catch on adjacent garments on a crowded rack, leading to pulled threads and damaged merchandise. Rust remained a latent concern. While nickel plating was effective, a scratch in the plating or prolonged exposure to humidity in a stockroom could allow corrosion to begin, leading to rust stains. For the retail employees, the work was tedious and presented a minor but real risk of finger pricks. For the customer, removing the tag was a small but tangible inconvenience. The process of pulling a sharp pin from a newly purchased garment was one that carried a slight risk of damaging the item or pricking a finger if not done with care. These were not dramatic, business-ending problems, but a collection of small, persistent inefficiencies and risks that, when multiplied by millions of transactions, represented a significant operational drag. The seeds of innovation were sown in this quiet dissatisfaction with the simple pin. The 1930s and 1940s were decades of economic constraint and global conflict, periods that often foster pragmatic and frugal innovation. The Great Depression forced department stores to focus intensely on cost-cutting and efficiency. Every penny saved, every minute of labor reduced, was critical. World War II brought material shortages, forcing industries to find alternatives to standard materials like steel and brass. These pressures accelerated the search for better tagging methods. One of the first significant alternatives to the pin to gain traction was the string tag. This was not a new invention. String and twine had been used for centuries, but its application in a standardized retail context was refined during this period. The string tag consisted of a standard cardstock tag, but instead of a simple punched hole, it featured a hole reinforced with a small grommet, usually made of compressed paper fiber or, less commonly, thin brass. A loop of fine, polished cotton string was passed through this grommet and knotted. The specifications for these components were carefully considered. The string was typically a 2-ply or 3-ply mercerized cotton. Mercerization is a chemical treatment that swells the cotton fibers, increasing their luster, strength, and affinity for dye. This resulted in a smooth, strong string that was less likely to fray or snag on delicate fabrics. The tensile strength was a key metric, ensuring the string would not break under normal handling. The other end of the string loop was designed for attachment. The most common method was a simple loop that could be passed through a buttonhole or around a thin strap or belt loop, and then secured by passing the tag back through the loop, creating a simple slip knot, often called a lark's head knot. This method was exceptionally gentle on garments, leaving no holes or marks. It was the preferred method for delicate items like lingerie, silk scarves, and fine knitwear, where a pin was simply too damaging. For garments without a convenient buttonhole or strap, a different method was needed. This led to the development of string tags with small metal clasps or pins integrated into the string itself. One popular design featured a small, sharp, V-shaped wire clip at the end of the string. The clerk could squeeze the clip, push the sharp point through the fabric at a seam, and release it, allowing the clip to hold onto the fabric. This was faster than a safety pin, but still required piercing the fabric. Another innovation of this era was the rise of the staple. Handheld staplers had become common office equipment, and their application in retail tagging was a logical extension. Specialized staplers were developed for this purpose. Unlike an office stapler that drives a staple through paper and clinches the ends flat, tagging staplers used a pin-type staple. This staple was driven through the price tag and the garment's fabric, but the legs of the staple were not bent or clinched. They remained straight, acting like a two-pronged pin. This was faster than using a T-pin, as it was a one-handed, single-action process. The tag was held against the fabric, and a single squeeze of the stapler attached it. However, this method had its own set of drawbacks. The staples, being relatively soft metal, could bend on thick fabrics. Removing them was often more difficult than removing a T-pin, sometimes requiring a special tool or risking a torn fingernail. The two holes created by the staple were often more noticeable than the single hole of a pin. As a result, staple-based tagging was most common on durable, heavy-duty items like work clothes, denim jeans, and canvas goods, where the fabric was robust enough to handle the attachment method without visible damage. The material shortages of World War II had a direct impact on tag and fastener specifications. Steel and brass were strategic materials, heavily rationed for the war effort. This led to a temporary decline in the use of metal pins, safety pins, and staples. Retailers had to rely more heavily on string tags. The quality of the paper tag stock itself was also affected. With resources diverted, paper mills produced lower-grade stock, often with less bleaching and no rag content, resulting in tags that were less bright, less durable, and more prone to tearing. These were sometimes referred to as victory tags. Inks were also of a lower quality, more prone to fading or smudging. It was a period of making do, reinforcing the industry's desire for better, more reliable, and less material-intensive solutions once the war was over. The collective experience of these decades solidified the understanding that the ideal tagging solution needed to be fast, safe for the garment, safe for the employee and customer, secure, and economical. The pin, the string, and the staple were all serviceable, but none of them met all of these criteria. The post-war boom of the 1950s ushered in an era of unprecedented consumerism and massive growth for department stores. Stores became bigger, supply chains became more complex, and the volume of merchandise moving from stockroom to sales floor grew exponentially. In this environment, efficiency was paramount. The manual, piece-by-piece methods of the past were becoming a significant bottleneck. The labor cost associated with tagging millions of items with pins or strings was substantial. This period saw the first serious, organized efforts by the retail industry to standardize and mechanize the tagging process. Retail trade groups, most notably the National Retail Dry Goods Association, or NRDGA, formed committees specifically to address the challenges of merchandise marking. These committees brought together executives from major department stores, logistics experts, and representatives from tag and equipment manufacturers. Their work was methodical and deeply unexciting. They produced detailed reports and guidelines on subjects like optimal tag placement for minimum fabric intrusion, and comparative time-motion studies of pin versus staple attachment. They developed standards for the layout of information on price tags, dictating the placement and size of the department number, the stock keeping unit, SKU, the price, and any promotional markdown information. These standardization efforts drove a desire for mechanical solutions. The dream was a tagging gun, a device that could attach a tag to a garment in a single, quick action. Early attempts in the 1950s focused on mechanizing existing fastener types. One type of device was essentially a magazine-fed T-pin applicator. It held a row of T-pins and, when actuated, would drive a single pin through the tag and fabric. These machines were often bulky, heavy, and prone to jamming. They offered a marginal speed improvement over manual pinning, but did not solve the fundamental problems of fabric damage. Another path of development involved more sophisticated stapling systems. Companies like the Monarch Marking Company and Kimball Company, which specialized in price marking labels and machines, developed heavy-duty industrial staplers. Some of these used fine wire-like staples that were less damaging than the standard flat staples. Some systems even used a staple made of a continuous filament of metal wire, which was fed from a spool, formed into a staple shape, driven through the garment, and cut in one cycle. This eliminated the need for preformed staple magazines, but required complex and expensive machinery that was more suited for a factory setting than a department store stockroom. Material science also began to offer new possibilities. The post-war era was a golden age for plastics. Materials like nylon, polystyrene, and polyethylene were becoming commercially available and were seen as wonder materials, lightweight, strong, and moldable into complex shapes. While plastics were not yet used for the fasteners themselves, they began to appear in the tags. Some companies experimented with plastic tags, particularly for items that would be exposed to the elements, like outdoor gear or sporting goods. These early plastic tags, made of materials like celluloid or vinyl, were durable and waterproof, but also significantly more expensive than paper. The fundamental breakthrough, the one that would truly revolutionize the industry, was still to come. It required a conceptual leap away from metal pins, staples, and strings. The solution would not be an improvement on an existing method, but something entirely new, born from the unique properties of modern polymers. The research and development in the late 1950s was laying the groundwork. Engineers at companies like the Denison Manufacturing Company, a major player in paper products and tags, were beginning to experiment. They were asking a different question. Instead of finding a better way to piece of metal through fabric, could they devise a system that used a flexible plastic filament? The challenge was twofold: how to form the filament into a secure fastener, and how to create a tool that could attach it quickly and safely. The meticulous incremental progress of the 1950s was setting the stage for the plastic revolution of the 1960s. The quiet dissatisfaction with the pin was about to be answered in a way that would permanently change the back rooms of every store in America. The 1960s marked the definitive turning point in the history of price tag attachment. This was the decade that the plastic fastener and the attaching tool, colloquially known as the tagging gun, were invented, perfected, and introduced to the market. This innovation did not merely refine the existing process, it rendered it obsolete. The leader in this transformation was the Denison Manufacturing Company of Framingham, Massachusetts. The development of what would become the SwiftTack system was the result of focused engineering and a deep understanding of the needs of the retail industry. The core concept, attributed to an inventor named Jack Farrell in the late 1950s and early 1960s, was to use a single, molded plastic filament to both pierce the fabric and secure the tag. This filament would need a sharp point for insertion, a method for locking itself in place, and a way to be dispensed from a handheld tool. The first critical decision was the choice of material. The engineers settled on nylon, specifically nylon 6/6. This polymer was an ideal candidate for several reasons. It had a high tensile strength, meaning it could withstand significant pulling force without breaking. It possessed a unique combination of stiffness and flexibility, allowing it to be formed into a thin filament that was rigid enough to be pushed through fabric, but flexible enough not to be brittle. Nylon also has a low coefficient of friction, a property that would prove crucial for both the needle's passage through fabric and the fastener's movement within the tool. Finally, and most importantly, it was exceptionally well suited to precision injection molding, the manufacturing process that would allow the complex shape of the fastener to be produced economically and in vast quantities. The design of the fastener itself was a stroke of simple genius. Instead of a simple filament, it was designed as a single piece with two distinct ends. One end was a thin bar, which would be called the T-bar. The other end was a larger, flatter shape, which would be called the paddle. These two ends were connected by a thin, uniform filament. The entire unit looked somewhat like a tiny plastic dumbbell or paddle. The idea was that the T-bar end would be inserted through the fabric and would then sit on the inside of the garment, its bar shape preventing it from pulling back through the small hole it had created. The paddle end would remain on the outside, too large to pass through the hole in the price tag, thus securing the tag to the garment. To facilitate manufacturing and loading into the tool, these individual fasteners were not molded one by one. They were molded in large clips, often containing 50 or 100 fasteners connected by a thin runner bar. This arrangement, which resembled a tiny plastic ladder, allowed for easy handling and a reliable feeding mechanism within the attaching tool. The injection molding process was highly precise. Molten nylon pellets were forced under high pressure into a multi-cavity steel mold. The mold contained the negative space of hundreds of these fastener clips. The nylon cooled and solidified in seconds, the mold opened, and the finished clips were ejected, ready for packaging. The second piece of the puzzle was the attaching tool, the gun itself. This handheld device needed to perform several functions in a single squeeze of a trigger. It needed to feed a single fastener from the clip into position. It needed to safely guide the fastener through the fabric, and it needed to separate that one fastener from the rest of the clip. The solution was an elegant piece of mechanical engineering centered around a hollow needle. The needle, made of hardened and polished steel, was the part of the tool that would actually pierce the fabric. It was sharpened to a fine, conical point to minimize damage. The key feature was a longitudinal slot running along its side. Inside the tool, a long, thin plunger was aligned with the hollow interior of the needle. The process, when a user squeezed the trigger, was a sequence of coordinated movements. First, a feed mechanism, often a small pawl or toothed wheel, would advance the clip of fasteners, positioning the T-bar of the very first fastener directly behind the hollow needle, in line with the plunger. As the trigger was squeezed further, the plunger would move forward, pushing the T-bar of the fastener into and through the hollow needle. The user would have already pushed the point of the needle through the price tag and the garment's fabric. The plunger would continue its travel, pushing the T-bar completely out of the tip of the needle on the far side of the fabric. At the same time, the paddle end of the fastener would be held in the tool, outside the garment. As the T-bar cleared the needle, the filament connecting it to the paddle would be stretched taut through the fabric. At the full extent of the trigger pull, a small integrated knife blade would swing past the feed mechanism, cleanly severing the filament of the now attached fastener from the runner bar of the clip. When the user released the trigger, the plunger and feed mechanism would retract, and the next fastener in the clip would be automatically positioned, ready for the next garment. The entire action took less than a second. It was a vast improvement over the old methods. It was faster than pins, strings, or staples. It was safer for the operator, as the sharp needle was the only point of concern, and it was typically used with a degree of care. Most importantly, it was gentler on the garment. The needle was extremely fine, and the nylon filament left behind was soft and flexible. The resulting hole was minuscule, far smaller and less damaging than that left by a T-pin or staple. The smooth plastic had no sharp edges to snag other clothing. For the customer, removal was simple. A quick snip with a pair of scissors was all that was needed, with no risk of injury or damage to the new purchase. The Denison SwiftAxe system was introduced to the market in the mid-1960s, and its impact was immediate and profound. Department stores quickly recognized the enormous labor savings and reduction in merchandise damage. A stock clerk who could previously tag a few hundred garments in an hour could now tag well over 1,000. The process became de-skilled. It required minimal training and could be performed with consistent results by any employee. The satisfyingly dull click-click of the tagging gun became the new soundtrack of the modern stockroom. The specifications for the system were, like everything that had come before, a subject of careful consideration. The standard fasteners were typically made in various lengths, from a short half-inch for attaching tags snugly to an item, to long 3-inch or even 5-inch versions for tagging pairs of shoes together, or attaching tags to bulky items like blankets. The filament diameter was standardized at approximately 0.05 inches, or 1.2 millimeters. The paddle was designed with a large enough surface area to display a brand name or logo, an opportunity for marketing that had not existed with previous methods. The T-bar was precisely dimensioned to be long enough to provide a secure anchor, but small enough to pass easily through the hollow needle. The system was not without its own set of minor operational challenges. The needles, though made of hardened steel, could occasionally break if used improperly on very tough materials, and they needed to be replaced. If a needle became dull or developed a burr, it could snag fabric, so regular inspection was necessary. The feed mechanisms could occasionally jam, particularly if a damaged or warped clip of fasteners was used. However, these were minor issues compared to the systemic flaws of the older methods. The plastic fastener system was, by any objective measure, a comprehensively superior solution. Its adoption throughout the 1970s was not just a trend, it was a complete technological replacement. The 1970s and early 1980s were a period of widespread adoption, refinement, and maturation for the plastic fastener system. The Denison-Swift Act had established the new industry standard, and the market shifted from one of competing fundamental technologies, pin versus string versus staple, to one of competing brands and subtle variations of the same core plastic fastener technology. Companies like Avery, which would later merge with Denison, and Monarch Marking Systems introduced their own compatible or competing systems, fostering a market of incremental improvements. One of the most significant areas of refinement was the development of specialized systems for different types of fabric. The standard tagging gun and fastener, while excellent for general use on fabrics like wool, cotton, and polyester blends, was still too harsh for the most delicate materials. The standard needle, though fine, could still leave a noticeable hole or pull a thread in fine silks, satins, lingerie, or high-end, lightweight knitwear. To address this, manufacturers introduced fine fabric systems. A fine fabric system consisted of a different tool and a different set of fasteners. The tool, often distinguished by a different color body, was equipped with a much smaller needle. A standard needle might have a diameter of around 2 millimeters, while a fine fabric needle would be closer to 1.3 millimeters. This required a corresponding change in the fastener. Fine fabric fasteners were molded from the same nylon material, but the filament connecting the T-bar and the paddle was significantly thinner, often less than a millimeter in diameter. The T-bar itself was also smaller and more delicate. Using this system allowed for the secure tagging of even the most sensitive garments, with a minimal, often invisible, mark. Of course, the thinner filament had a lower tensile strength, making it unsuitable for heavy garments, so stockrooms now needed to maintain two separate systems: the standard system for the bulk of their merchandise, and the fine fabric system for their high-end and delicate apparel. At the other end of the spectrum, a need also arose for heavy-duty systems. Standard fasteners could sometimes fail when used on very heavy or dense materials like leather coats, area rugs, or thick upholstery. The nylon could stretch or even break under high stress. To solve this, manufacturers developed heavy-duty or T-end systems. These tools were more robustly built, often with all-metal mechanisms, and featured a thicker, stronger needle. The fasteners for these systems were different as well. They were often made not from nylon, but from polypropylene, a polymer that is more rigid and less expensive than nylon. The filament was much thicker, and instead of a paddle, both ends of the fastener were T-bars. This allowed the fastener to be used for pairing applications, such as holding a pair of heavy work boots or gloves together for display. The design of the tools themselves also evolved. The first-generation tagging guns of the 1960s were effective but often heavy, with cast metal bodies. Through the 1970s, there was a clear trend towards improved ergonomics and lighter weight. Tool bodies began to be molded from high-impact ABS or polycarbonate plastics, which were strong, durable, and significantly lighter than metal. Handles were redesigned to better fit the human hand, reducing operator fatigue during long shifts. The trigger mechanisms were refined to require less pulling force, and the internal feed mechanisms were improved to be more reliable and less prone to jamming. The fasteners also saw subtle innovations. While the basic T-bar and paddle design remained the standard, the paddles began to be offered in different shapes and sizes. Some were made round, others square or rectangular, allowing retailers to choose a shape that complemented their branding. Color became another variable. While the vast majority of fasteners were made from a natural, translucent nylon, they could be produced in any color. This was used for inventory management and security purposes. For example, a store might use red fasteners to indicate merchandise that was on final clearance, or a specific color to denote items from a particular season or supplier, making visual identification in the stockroom much faster. The logistical impact of this mature system was immense. The pre-loaded clips of 50 or 100 fasteners streamlined the entire workflow. Instead of handling thousands of individual sharp metal pins, a stock clerk handled clean, safe plastic clips. The speed of the process allowed for a more responsive inventory system. Goods could arrive at a receiving dock in the morning, be untagged from their shipping packaging, and be retagged with the store's own price and security tags using plastic fasteners in a matter of hours, ready for the sales floor the same day. This velocity of merchandise processing was a key component of the increasingly competitive and fast-paced retail environment of the late 20th century. By 1980, the evolution was largely complete. The plastic fastener system had achieved total market dominance in the American department store. The T-pin, once the universal standard, was now relegated to niche uses in tailoring or for display purposes. The string tag still existed, but primarily for hard goods like housewares or luggage, where there was no fabric to pierce and the string could be looped around a handle. The staple was all but gone from apparel tagging. The meticulous, decades-long journey from a sharp piece of steel to a sophisticated polymer-based system had reached its destination. It was a silent revolution, one that was invisible to the average shopper, but fundamentally reshaped the operational backbone of the retail world. It was a testament to the power of incremental improvement and the relentless, if unglamorous, pursuit of efficiency, safety, and standardization. The simple act of looking at a price tag had been made possible by a long and profoundly boring history of material science, mechanical engineering, and logistical refinement.